In this tutorial we are going to be talking how to create wavy texture for wall panel. Based on the points that are randomly positioned on the wall, we'll be able to push away the corner points of the curve which are used to generate the wavy texture. Once we make the curves, we'll use them as a rails for sweep 2 in order to create carving effect. Without further ado, let's get started. Hi guys, Lazar here. This is the final shape that we are going to create in this tutorial, but for now I'm going to turn this off and I will disable this part. Okay, and we'll start with the point. Once you place the point on the canvas, right click and click set one point in order to generate this guy. In the second step, we'll create the second point, and based on these 2 points we will create the line. Using point polar, we will create that second point, and we need 2 inputs here. The first input is the distance from the original point, and this is the angle in radians. So once we place in the XY the angle in radians, you can see we can rotate this one, and here we can set the distance. I'm going to place as it was before, something like this. And once we have these 2 points, we'll create the line. Now we'll move this line along a z-axis. So the start point will be 0, and the end point, or the end coordinate, will be 40. So that's why we'll construct a domain from 0 to 40, and within this domain we'll generate 24 divisions or 25 equally distributed numbers. And once we generate these 25 values equally distributed, we'll place in the z vector. Z vector will be placed in T, and in G we'll plug this line. Once we turn this on, we have 25 lines. The next step, we'll divide these lines using divide curve. Once we divide these lines into 25 divisions, we'll get 26 points. And now we will take out, let me first place param viewer here. So we have branches from 0 to 24. Now I'm going to take out the points from the first branch, or from the first line. We know that these points are placed in the branch 0, and also I'm going to take out the points from the last line, or from the last branch, and we can see here the last branch is 24. So I'm going to place them in a separate list, and the rest, so the points from the branch 1 to 23 will be in another tree, in another list. Okay, so how we can create that? So first, these points I will place in the tree statistics, and in the P we can find all the paths of the tree from 0 to 24. Now I'm going to use a list item and the call index. In the list item, so in the L, I will place all the information from this panel, and in the I will place numbers 0 and -1. It means that the index 0 will be placed here, and if we place -1, it means the last index in the list will also be retrieved from the list. So as output we have path 0 and path 24. The same logic I will use for the call index. So, but I'm going to remove these two items from the list using the same logic, 0 and -1. And you can see here we have the paths from 1 to 23. Okay, so now in the tree branch component, in the P we'll place these paths, and in the T we'll place the output P from the divide curve, or these points. If I turn this on, and you can see here that we managed to take out all the points that are placed in the branches from 1 to 23. And in the other part of the script, we will use these two branches. So the branch 0 will be placed here, and the branch 24 will be placed in this component. We will use this later. Before we do that, I'm going to create the surface using the lines that we move along z-axis. So these lines will be placed in the loft, and that's how we can create the surface. This surface will be randomly populated with the points using populate geometry. So in N, we'll set how many points we will populate on the surface. This is the iteration number. And in the P should be placed pre-existing population. We will use this input because we don't want to create the points that are close to these edges. So with that purpose, we will place pre-existing points, and these pre-existing points we will get placing the surface in the curve container, and now we will populate this curve with the points. That's how we get randomly positioned points on this boundary curve. Here we can define how many points we'll have, and these points will be placed in the pre-existing population. If I turn this on, you can see that we don't have points that are close to the edge. And that's how we get these populated points. Now I will turn off these lines, and I will turn on these points from the branches 1 to 23, and I will pull them to these randomly positioned points. So for that, we'll use pull point. In the P, we'll place these points, and in the G, we'll place populated geometry. And if I turn this on, we have basically this populated geometry. But what is important here, which is not visible, that we have the same tree structure as we have here. So basically, each of these points are pulled to their closest populated points. For example, this point, it's pulled here. This guy, it's pulled here. This one, it's pulled here, and so on. If I create line, we'll get something like this. All these guys have the same randomly positioned point that are closer to. You may notice that I check here principal. It means the output here will keep the same path numbers as we have in this input from 1 to 23. That's why I check principal, because I want this output to have the same tree structure from 1 to 23. If I didn't check principal, the output here will be from 0 to 22, which we don't want. Once we get these two set of points, we will create the vector using vector 2point. So in A, we'll place these pulled points, and in the B, we will place these original points. Once we get this vector, I'm going to visualize it using vector display. In the V, I will place the vector 2point, and in the A or the anchor point, I will place these pull points. If I turn this on, these are the vectors that we get. Okay, now I'm going to deconstruct this vector. As we know that vectors are can be deconstructed into x, y, and the z vector. We are going to do this now using deconstruct vector and taking only a z component on the vector. For example, if we have this vector, it can be deconstructed to z1, and in this case either x or y, I'm not sure, but we need just this guy. So we'll take only that component of these vectors, and then we will construct a new vector using only this guy. And if I display this vector again, we'll get only vertical vectors. We need this because we're going to move the original points based on these vectors. Now we need just to create vector amplitude, and the vector amplitude we can take from the L, or the length of the vector 2 point that we previously created. For that, we will use remap component. So L, or the length of the vectors, will be placed in the V. The source domain will be bounds based on these vectors, or based on the length of these vectors. So we basically will get 24 domains, and all these values will be deconstructed from 0.8 to 0, meaning that the closest point will be pulled to 0.8 and the furthest will stay in the same position. Why we are reversing this? Because we want to push away the most point that is closest to the populated point. So if we have this this original point that is closest to the populated point, this guy will be moved to along z vector or minus z by 0.8. Once we get all these values from 0 to 8 in each branch, we will place in the vector amplitude. The vector we previously created using only z component. And once we get all these vectors, we'll place in the T, and in the G we'll place these original points. Once I turn this on, we get pushed points from the populated points. Now we can create the curves from these points. Okay, but there is one step in between. But there is one step in between. As you remember, we have branches from 1 to 23. Now here we want to place branch 0, and here we want to place branch 24. So using a merge component in the D1, we'll place points from the branch 0, and here we'll place points from the branch 23. I forgot to explain why we taking out first and last set of points, because we want to keep the straight edge of the final shape. So if we didn't taken out these two set of points, the final output will go something like this or something like this. But we want to keep straight or unmodify this. So that's why we excluded this from the modification. Once we place here, now you can see that we have 25 branches from 0 to 24. Once we created the curves on the flat surface, we need to find a way how we can create that carving effect. We have curves, so this is curve with the index 0, with index 1, 2, 3, 4, and so on. The idea is to create that kind of data structure that will have curves 0 and 1 in the branch 0. Then in the branch 1, it will have curves 1 and 2. In the branch 2, it will have items 2 and 3, and so on. In order to get that kind of data structure, we will use shift list. If you use -1 with the false value for the wrap, basically we will take out the last item from the list, and we'll keep items 0, 1, 2, 3 until 24. This is when we have -1 with the false. If we have 1 with the false, we'll create the list in a way that will remove the first item from the list, or the items with the index 0. Basically, item with index 1 from the original list will have index 0 in this one. So it will have 0, 1, 2, 3 up to 24. So this guy here, this line will have index 24. Okay, once we have this kind of data, we'll graft each list and then we will merge them. So in the branch 0, we'll have these two lines, because for the -1 shift list, this is index 0, but for the 1, this is index 0. And this will be placed in the index 0. In the index 1, we'll have this line, and so on. Let me visualize this. So this data. So these two curves are in the branch 0. If we change this one, these are in the branch 1, the branch 2, these two curves, branch 3, these two curves, and so on. Okay, now I'm going to find the start point of each curve using endpoint. Start curve will have 2 points, meaning that the start point from the first and the second curve, one start curve, this will be another start curve. These 2 points will be used in the construction of the arc. There is a component arc 3 points. This will be point A, this will be point C, and the point B we need to generate. So how we can get that? As I said, this will be A, this will be C, but for the B, we'll first create a line between these two guys. Once we create the line, we'll take out the middle point, and then using ease planar component for the surface, we will create this plane. So this is X, this is Y, and this will be Z vector of the plane. This vector will be used in order to move middle point of this line. So we'll use this vector to move along here, and that's how we are going to create a B point for the arc 3 points. So this is A, this is C, and that's how we can create the arc. Let me show you in the script. Once we create a line using point of curve, we'll find the middle point, and now we need to find the vector using ease planar for the surface. We'll get the plane. That plane will be deconstructed, and this vector will be placed in the amplitude. In the amplitude, or the A input, we need to find for how much we are going to move at this point along Z vector. And this will be based on the length. So, for example, this length is not the same as, let's say, this one. So we're going to calculate the list length. Then, based on the length, we will remap these values, and we will remap within domain 0.3 to 0.4, meaning that the middle point placed on the largest line will be moved along Z vector for the 0.8, and the middle point that are placed on the smallest line will be moved along Z vector for 0.3. And we can see it here. Using length, we'll calculate the length of these lines. Then this length will remap in 0.3 to 0.8, and the result will place in the amplitude. Once we get the vector, we'll use it to move this middle point. Let me turn this on. Okay, and now this guy will be placed in the B. That's how we created the list of arcs. In one of the last steps, we need to create the surfaces, and that we'll get using sweep 2. So the rail 1 will be the first curve in the list, or the curve with the index 0, and the curve with the index 1 will be placed in the rail 2 section. Will be the arc, and once I turn this on, we get that wavy texture. If you want to get the thickness of this wall, basically we just can extrude this flat surface. from the start of the script. We'll extrude it by let's say 4, and we'll use split BWrap component. So this box will split with this BWrap, and we have 24 BWraps, but we want to keep the one with the highest volume. So that's why we can generate the bounding box of each BWrap in the result, calculate the volume. We are going to sort this result based on their volume. We will reverse the list, placing in the descending order, and the first item in the list we are going to take out. And let me turn on these guys. I'm going to turn on the surface, the BWrap with the highest volume. And once we have these two guys, we are going to merge them and to join in a single BWrap. And this is how we get this wavy ball. For all of you who would like to go a step further, I created an extended tutorial which is more advanced because it combines sine wave within mathematical expression with attractors, either curves or points. Also, you will learn how to exclude control points that are closer to the edge in order to keep rectangular final shape. This you can watch on our Patreon page and support our work at the same time. With that, you will also get access to all our extended tutorials and project files. Before I wrap this video up, I would like to share something with you. If you're in architecture and you're interested in learning more about Rhino and Grasshopper, but you're tired of searching through thousands of tutorials online and wasting so much time doing that, and you're looking for a structured learning approach with one-on-one support, we created a course called Rhino for Architects that will guide you through all of the basics of both Rhino and Grasshopper. In addition to that, we'll be covering some advanced modeling techniques using sub-D division tools for Rhino 7, which will allow you to create any kind of geometrical shape that you imagine. When it comes to Grasshopper, we'll explain every single essential component with examples and homework files, so even if you're a total beginner, you'll be able to understand the logic and mathematics behind the program. On top of that, we'll teach you all about various plugins for Rhino that are used in architecture, such as Vray, Visual Arc, and even Bongo for architectural animation. Lastly, we'll cover architectural presentation, creation of diagrams, and couple of case study projects. If this sounds like something you would like to check out, feel free to schedule your free Zoom call with us in the first link in the description. On this call, we will evaluate your current skill sets, determine if this course can help you out, and on top of that, we will share our learning platform with you so you can get better idea how all of that looks on the inside. Click on the link below the video and we'll talk soon. Take care.